Welcome back. Today we're talking about ECG. We're talking about cardiac cycle as well. So let's just dive right into it and like and subscribe. So let's just draw a map of the heart. Obviously we have atria, ventricles, and things, but let's talk about the SA node. The SA node is where all this propagation and for depolarization things begins. So I kind of want to draw. So if you know anything about physics, we have vectors, direction and magnitude, right? And we represent them as arrows. This SA node is kind of propagating these charges, these positive charges throughout the heart. And it's not necessarily certain parts, because there are like myocardium that surges throughout the heart that charges could pass through, but positive charges that are getting represented and passed out through the whole heart. We could draw an average vector like this through the heart, and that's kind of the directionality of the charges through the heart. And so if we have some nodes right here, this could be called lead 1. So now, as you know from previous videos of mine, or maybe on YouTube, or things that you've learned before, we know that we could track these charges and these action potentials sent throughout any type of organ, especially. You could do that with the heart. And so when we put tags right through the body like this, that's called lead 1. We could have lead 2 up top, and there's 12 different leads. But when an action potential is sought out, we could kind of see it like this. We could kind of see a depolarization and then a repolarization, right? And just like anything else. But it's always graphed as a graph like this, because if you think back in the day, and ECG was built first with a piece of paper and a machine connected to the piece of paper with a pen, and the pen or the paper would move, and the pen would, if it tracked a certain point up top, then it would move to up top, and it would move down bottom, right? And that's how it would make. So that's kind of why we have this line notion of things. And that's how we do action potentials. And from these action potentials and this data that we could receive, we can make a graph. And it's this certain type of graph you may know. And it looks like this. You probably recognize this. This is an ECG. Now in ECG, we alphabetize the ECG, and we alphabetize some of these waves. So the PQRST parts of the wave. So we kind of have, we split them a little bit differently. Like we have the P, and then we have the QRS complex, and we have the T wave. But again, it's from depolarization or repolarization, depending on what's going on. And this is how we track it. So let's just go right into it. So the P wave is atrial depolarization. The atria is contracting, and it's depolarizing. It's gaining charge, obviously. And so because of that charge, remember in my past videos with muscle contraction and things, calcium floods in. As calcium floods in, heart can keep going. So, for example, in the sympathetic nervous system, norepinephrine can be released, and beta-1 adrenergic receptors increase the influx of calcium. And then norepinephrine can also we could talk about like an increased relaxation rate, or lusitropy, which these same beta-1 adrenergic receptors increase calcium, a reuptake into the sarcoplasmic reticulum. And then we have an increased heart rate from beta-1 adrenergic receptors, increases the current, faster pacemaker potential. Anyway, so we have this atrial depolarization at the P wave. And then the QRS complex is mainly the ventricular depolarization. And so the charges move throughout, or the contractions move throughout the body, or the heart, from the atria to the ventricles. Atria contract first, ventricles contract second. Atria pushes blood into the ventricles, ventricles pushes blood to wherever it's going, right? If it's the left ventricle, it's pushing blood throughout the body. Right ventricle is pushing blood into the lungs. So there's some types of determinants that we could talk about with the ECG. So with the ECG, we could see many different things. We could see heart rate. We could see what's going on with ventricular depolarization. Maybe ventricular depolarization is not happening as well as it should be. So sometimes we kind of see this thing happen like this. So notice here we have something wrong in this area, right? That does not look like this at all. And this is kind of what we call, because you can't really see it this super well, but we have an S and a T wave. Now it's called ST elevation. And so this is what we call STEMI, right? ST elevation, myocardial infarction. Myocardial infarction is a heart attack. And so to explain what's going on with an ST elevation, myocardial infarction, we kind of have to talk a little bit about coronary arteries. And so let's just kind of zoom in to the heart, into the ventricle at least. So this is the ventricle, aorta is atria is up there. We have, I'll draw this in red, we have a thing called a coronary artery. And coronary artery is very cool because it's blood that feeds itself, right? We have, the heart needs the oxygenated blood, we need troponin, we need things going on throughout the body. But it does it with residual blood. So as blood leaves the left ventricle, the valves close, and sometimes there's blood that comes back. Instead of going back into the ventricle, it falls into these things called coronary artery. And this coronary artery kind of sits like this. And again, I'm not the best drawer or anything, but this will explain to you the best type of things we need. So we have here this coronary artery. Coronary artery goes in and it branches off and it feeds the myocardium of the heart. And we have these other things called endocardial myocytes. So there's these cells right here. I'll just call them cells. They're within the cardium, or the muscle of the ventricle, the myocardium. And they need blood. And pretty much within this, there's a channel that we know all too well, and that is the sodium-potassium channel, most important channel in the body. And this sodium-potassium channel, as we know, needs ATP. And this comes from the blood. And so as we see a decrease in ATP, we see a decrease in the usage of sodium-potassium channels, which does not help with contractivity. And so what actually happens, each of these cells actually has a negative charge to it. And so this changes, again, we have leads and things and how we're tracking action potentials and electron gradients throughout the body. It changes, and that's how we kind of get this NSTEMI going on. So what really happens with, STEMI. What really happens with STEMI is after some time, we have kind of a blockage. And this blockage fills up, it's with plaque and stuff. Blood can't get through there. And so the blockage usually, it can sometimes, I don't want to say always, doesn't just pop up right there. It eventually takes some time and then it will close. But as it starts closing, there's more cells here that start to grow because they need ATP and they're not getting, because the blood's coming through here and these are getting the blood first. So this is the most common area for this ST elevation myocardial infarction to start. And so it has these negative charges that are propagated, and it changes the average vector. And so therefore it changes the depolarization and things of the ECG. So we have STEMI, this ST, elevated myocardial infarction, but we also have non-STEMI, which is non-ST elevation myocardial infarction. And this is actually due to a partial blockage in the coronary artery. So if this was just like partially blocked, so it's still kind of causing this issue going on, and it elevates cardiac enzymes like troponin in the blood, but in the ECG we do not see an ST elevation. Versus an ST elevated myocardial infarction, we have a complete blockage of the coronary artery and elevated cardiac enzymes, and obviously an ST elevation. So let's go through. So this is just one of the bigger things. You're right. This is for medicine purposes, to know STEMI and stuff. Like, obviously, I'm not expecting you to be 100% certain about STEMI and whatever, but I just kind of wanted to explain STEMI because that is something that happens. I want to say on a regular basis, but it happens a lot. So, okay, so it's all about the ECG. And we're going to kind of talk about the pressures within the heart and how the heart starts pumping all these things and what's going on. And so it all starts in the atria. The atria depolarizes, ventricles depolarize, and then the ventricle repolarizes, right? So let's kind of explain it with a graph. I don't know if I can. Here, I'm just going to erase this. I want you to remember this, but we need to erase it. Okay, so right here on this y-axis, we have pressure. And I'm going to draw the atria, or the left atria, I should say, and the left ventricle. So this is just kind of a key what's going on here. So the pressure in the left atria stays like this, and then atrial depolarization happens. As atrial depolarization happens, we kind of imagine like a toothpaste bottle. When you squeeze that toothpaste bottle, it's closing the bottle and it's pushing toothpaste out. But why? Because you're putting pressure on all the stuff within the bottle, or the tube, whatever you want to say, because you're kind of decreasing the volume. So that's kind of what's happening with the atria. Is the atria is contracting, it's contracting less volume, increasing pressure, pushing all the blood out of the left atrium to the left ventricle, filling it up. So we kind of have this little loop right here. Does that loop look kind of familiar to the P wave? Yes, it does. That's what's happening with the left atria, is the P wave represents atrial depolarization. As atrial depolarization happens, we kind of have this happen, and then the atria kind of also increases pressure here, and then it flatlines a little bit. But as this happens, we have left ventricular pressure. Left ventricular pressure is, I want to purposely draw it slightly below left atrial pressure, because there are points, and again, this is all happening boom, 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 fast. But as the pressure increases in the atria, the pressure will increase in the ventricle as well, because the atria is pushing blood into the ventricle. Ventricle's increasing pressure because there's stuff getting filled in it. But the ventricle will then just significantly increase pressure. And this is called isovolumic contraction. I'm just going to call it IVC, isovolumic contraction. And isovolumic contraction hits we have a significant increase in pressure, all the valves close, and then we kind of have this relaxation stage of the ventricle. So the ventricle is relaxing, it's just full blood, but that's not the purpose of the ventricle. The purpose of the ventricle, at least the left ventricle, is to send blood throughout to the whole body, right? So it shoots blood throughout the whole body, and we have a decrease in pressure because it's shooting blood out through the body, and then it goes like this. And then we have here, it all starts back up again. And over and over and over again. So, isotonic contraction, all the channels close, ventricle relaxes, blood gets shot out, and pressure decreases. But if you look at my key, I also wrote the aorta. Like, what are you doing there? So we can also draw the pressure of the aorta. It kind of decreases here, and then it will increase with the left ventricle because all the blood's going right into it, right? And then it comes down, and it bumps like this. So that's the aortic pressure. And so I'm going to label some things with black. So when you go to the doctor has the stethoscope, right? And stethoscopes, it just looks so cool when they come in, you know? And they have you sit, and they put it on your chest or on your back, and they have you breathe. And what are they listening for? You probably do know this because you're either interested in medicine or you've watched some movies and things. They're listening for lub-dub, lub-dub, lub-dub. And they're listening to see what's going on with the heart. So actually, we could see that here in this graph of pressure. So right here is lub. And right here is dub. And then we could also call this the dicrotic notch. So that's what's happening with blood dub. And you might be like, well, so what exactly is happening? That is a very good question. So lub, atria is contracting, right? Atria contracts. There's atrial depolarization, and we have all the blood going from the atria into the ventricles. And so that kind of makes a noise because that's a lot of blood, you know. And then dub is when, so we have all this blood going into the ventricles, and then the ventricles are also contracting and depolarizing and shooting blood out of the ventricles. But remember, I was talking about that coronary artery earlier. So it's happening pretty fast, and there's a lot of force actually happening throughout the body. And so there are valves between the atria and the ventricles, and the reason why these valves open is due to pressure, dependent on whether or not the pressure is higher in the atria or the ventricle. And so if the pressure is higher in the atria, the valve's going to open and shoot stuff into the ventricle. So once the ventricle shoots out, those doors close because it's significantly right here. The doors close, the pressure decreases significantly below the left atria, and all that blood comes back, but it goes into the aorta. But remember, there's some residual blood that comes back, and it just slams against that door, and it closes the door, and that's kind of the dub sound. It's just that residual blood slamming against the door. And so there's a couple things that we could see with lub-dub. And there's some things that the doctors are hearing for when they hear lub-dub. And I'm going to tell you that after I get some water. Okay. So there's some things that we could actually see with lubs and dubs. But I also want to talk about the volume of the heart as well. So I'm going to talk about lubs and dubs right over here. So the normal heart sounds lub, dub, 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 right? Boom, 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 boom. But sometimes when they put the stethoscope on you, they might hear other sounds. I hope they don't, but they might hear other sounds. And we could represent them like this. And this is one sound, lub, sh, dub. And this is a heart murmur. And a heart murmur is due to the fact that the valve's not closing all the way, and so some residual blood is going back into the ventricle. So heart murmur is pretty, like, it's not, I don't know. That's a heart murmur. And then sometimes we have lub, dub, right? There's a little gap in between, so this happens right before the dub. And this actually comes from the, it's like an aortic stenosis, an aortic stenosis, and the door or the valve isn't closing fully, the valve's not shooting blood through as best as it can. And sometimes we also have lub dush. This is like a leak in the semilunar valve. Leak in the semilunar valve, blood's getting pushed back through the semilunar valve. That's going to be happening. That's what this is. And then if it was like lubsh, dubsh, there's 2 leaks. Or lubsh, dubsh, or lubs, break, dubsh, or dubsh. There's a hole, or, there's different things going on. So, but those are like the more important ones that I just told you about. Let me erase those really quick. We have pressures, and we've already done pressures, but within the pressures, pressure and volume are somewhat related. So we have here, say, the volume of the ventricle. And I did ventricle in blue, so let's do blue. And the volume in the ventricle increases as the aorta tops it off. So it's like this. And then during isovolumic contraction, it stays right here, stays flat, and it just stays flat. So again, we need to understand that the atria only tops off the ventricles. We're not filling it. So that's why the volume, say the volume right here is, I think it's 120 milliliters usually. So the volume does change, but it's not 0. 0's, roughly down here. Say 0's right here. So the aorta actually is just topping it off. And I do want you to see that the commonality between the pressure and the volume. Left ventricular volume, at least. Milliliters. I do want you to see it mapped out the same. So again, the atria is pumping blood into the ventricle, topping off the ventricle. And then the ventricle, during isovolumic contraction, nothing's really happening. And we actually call this EDV. So I'm just going to draw EDV right here. I can't right now tell you what EDV stands for. You can look it up. But let's just call it EDV, and that's fine. And so isovolumic contraction hits. As the ventricle is relaxing, the volume is about the same. But what's the purpose of the ventricle? Is to shoot blood out through the body. So then the volume significantly decreases all the way down, and then it will round back up, and then it will kind of cause this little, like this. And we call this down here ESV. And you're like, well, Jackson, why are you telling me this just these random letters? And I'm like, I don't actually know. I'm just joking. We're going to talk about mean arterial pressure. Now, mean arterial pressure is important as we know the pressures throughout the body. And so we kind of we could make a equation. So mean arterial pressure, MAP, is equal to cardiac output times peripheral resistance. So I didn't speed that up or anything because I need you to know that's mean arterial pressure, cardiac output, peripheral resistance. And so cardiac output is actually stroke volume times heart rate. And stroke volume and heart rate are important for cardiac output, obviously, because what's the heart doing? But stroke volume is actually EDV minus ESV. Sorry, I'll just. So now we know, because of the volume in the left ventricle, the pressure in the left ventricle, we could actually calculate mean arterial pressure. We could use EDV minus ESV to calculate stroke volume. We could take the heart rate. That makes cardiac output and then peripheral resistance. So at the beginning of this lesson, I probably should have talked about myocardium and the strengthening of myocardium. And so usually, if you think about it, you want to grow muscle, and there's a huge gym culture about growing muscle and getting gains and things. But in the heart, the muscle in the hearts, we don't really want it to increase a ton. And that's what we call heart failure. Is if we have this heart and we have these ventricles, this is where the blood fills up, and it has a definite volume and shape. But this is the myocardium right here. If the myocardium gets bigger, increases, then we have, let me just draw it again, less volume, greater space for the myocardium, less volume for the heart. So it decreases stroke volume. As we decrease stroke volume, we decrease cardiac output. If we decrease cardiac output, we decrease mean arterial pressure. We decrease mean arterial pressure, it's a hard time for the body to get things out throughout the body, and could cause a lot of problems. So how does that happen? And this is what we call heart failure. But how does that happen? It depends. There's many different things. Sometimes it's just the increase of blood vessels. Sometimes that's why obesity is a problem, because as someone gets bigger, more veins have to grow, and the heart has to start pumping more, increasing myocardium, which increases stroke volume, which increases or decreases mean arterial pressure. Like, there's all sorts of things going on. So it's important to understand exercise is good. Exercise will affect the heart, but because it will increase stroke volume. As we increase stroke volume, this still needs to get filled with a lot of blood. And so this muscle will increase, but it'll actually just make the heart bigger. And the ventricle will stay the same. But if the heart isn't increasing stroke volume, then the ventricle is just going to get smaller. And that's the way the muscle's going to grow. So if we want to be in peak athletic performance, going peak heart rate is sometimes good, but not always good because of that. And yeah, so I just explained ECG. I explained what P, QRS, T waves are. I explained STEMI and NSTEMI. I even explained beta-1 adrenergic receptors. So if you didn't get all that, and the cardiac cycle as well, if you didn't get all that, I'm sorry. Comment below, email me, whatever. I'll explain it to you later. So have a good day, and we'll see you next time.